What if our solid really wasn't solid? I drew this at home last night for you. This is the region. This is the region bounded by y equals 4 and y equals 6. And the y-axis and the x-axis, and we're rotating it around the line y equals 3. So play like we don't know calculus, which may not be a far stretch for the trail. No, I'm kidding. We can find the volume of that cylinder without using calculus because we have a geometric formula for volume of a cylinder. And that's where I was supposed to be going, not even using calculus for this, but the volume of that thing will be the volume of the big cylinder minus the volume of the small cylinder and again, not using calculus at all. How do you find the volume of a cylinder? Pi r squared times the length. So this cylinder has volume pi times what's the radius of that cylinder. If you take the whole radius from y equals 6 to y equals 3, that circle would have, or that cylinder would have a radius of what? 3. All right. So pi r squared times 6. And the volume of the small cylinder would be pi times what is the radius of that core we're cutting out. All right, which is just the 4 minus the 3. And the length is still 6. So this is our radius of the big cylinder. And this is the radius of the small cylinder. And this is still called a solid of revolution, even though it has that core cut out and it's not really solid. It's formed by rotating a function around an axis, so it's still called a solid of revolution. And the volume of that solid, let's just factor out a 6 pi here. 6 pi, and we would just have 9 minus 1, where 9 is the radius of the big cylinder and 1 is the radius of the small cylinder. So the radius of that whole thing is 48 pi. Now that was just using geometry and a formula that we have from geometry, but the formula for calculus is very similar to that, in that we are going to have to subtract the radius of the inner function from the radius of the outer function. It's still going to be outer function minus inner function. So for example, what about this, which does take calculus? It's not a geometric solid that we know a formula for. What integral would give the volume of the solid formed by rotating this big function r of x? R of x looks to be a linear function in this case. If we're rotating that from A to B around this horizontal axis of revolution, but then we let this maybe quadratic, I'm not sure what that piece is, but if we let that piece bore out the center, then what would give us the volume of this solid that's formed? Solid, which is not really solid because it's got a hole cut through the middle. What do you think? How have all of the integrals that we've done with the disk method started? Pi times the integral. Our functions are functions of x, not functions of y here. So we're going to integrate with respect to x. and our limits of integration have to be x values. So what are our x values over which we're integrating here? From A to B. And what is our outer radius of this thing being rotated? Well, they're both R of X. This one's capital capital R of X is the linear one. Little r of X is going to be what's boring out the center. So what am I going to have to integrate? The outer radius the outer radius squared minus the inner radius squared. And Aaron, we're almost to your question now. Here we had to square both the little radius and the big radius before we subtracted, because we were getting the area of the big cylinder. We had to find its area by squaring its radius. We found the area of the little cylinder by squaring its radius, and that we're squaring those individually. Now that's different than the problem that we were asked about, or that we asked about, what was it, number 19 in last night's homework. Number 19 was really a solid. Its radius was affected by the fact that we were rotating it around a line other than the y-axis, but it was still a solid. We weren't boring out the middle, and that's why we ended up with that radius just being 5 minus y, and we were squaring that radius. It's when you have a hole being bored out through the center, that's when you're going to square each radius individually and then integrate the difference. All right? So if you have a true solid, then the formula is just basically pi r squared. But if you have a solid that has a hole bored through the middle, then it's outer radius squared minus inner radius squared. You're finding the volume of the big solid and subtracting from it the volume of the little solid, so you're squaring both of those radii. Does that help with the question you originally asked? That on number 19, 5 minus y was the radius. But in this example, the volume is going to be the big radius with the middle board out. All right, let's do some examples. Got a bunch of them, 7, I think. Number 6. Number 6, we actually have the graph already. We just have to set up the integral. Based on this image, it looks like we're going to rotate this region around the x-axis. And when we're rotating around the x-axis, we're using rectangles perpendicular to it. We're using vertical rectangles, and vertical rectangles have the width dx. So we need to integrate a function of x. Our limits need to be x values. But I can see that when I rotate that around the x-axis, I'm not going to have a true solid. I'm going to have a solid with a core removed from it. So in that, Tell me what the outer radius would be given by.
4 minus x squared over 4.
It's obviously this quadratic one. The outer radius is 4 minus x squared over 4. And what is the inner radius being bored out? Actually, hold on one second. No, that's right. What's the inner radius that's being bored out? From here to here, 2. Oops, sorry. So the volume of the solid being created is pi times the integral from where to where? -3 to 3, x values, since we're integrating with respect to x. And then the outer radius squared minus the inner radius squared. And integrate all of that with respect to x. And I'm less worried about the algebra here and your ability to do that definite integral. So like yesterday, we're just going to set up the integrals. The ones in the homework, I tell you whether to find the exact value or approximate. So on this one, if I just say approximate it, then you calculate this value on your calculator and tack a pi on there. And that's it. Okay. I got one without making a mistake. Don't be a smart ass.
Oh.
I'm kidding. I'm kidding. All right. So what about one that's not graphed for us already? Number 12. A part. We'll do the A part and the C part, but the A part is rotating this quadratic function around the y-axis. What does around the y-axis automatically tell us? Horizontal rectangles. And horizontal rectangles have a width of dy. Which means at some point we're going to have to solve that equation for x because we're going to have to integrate a function of y. We need a function of y and we need our limits being y values. So you don't have to write that down if you don't need it, but it helps me. Let's see what the graph looks like. Y equals 2x squared, bounded by the x-axis and the vertical line x equals 2. That means we only need to graph it up to where x equals 2. When x equals 0, y would equal 0. When x equals 1, y would equal 2. And when x equals 2, y would equal 8. So here's that piece of parabola we're going to be rotating around the y-axis. Notice that if we rotated this around the x-axis, it wouldn't have a hole in the middle. It would just be a solid. But because we're rotating this around the y-axis, it is going to have that hollow center. Now, what's our outer radius? In terms of y. Imagine this, I have to try to picture this in my head. And let me tell you this, when I picture it rotating, it sounds like my washing machine. It does in my head. I'm hearing. I'm sorry, now y'all will. Yes, the outer radius is formed by this vertical line. It also helps me when I write r of y to remember that that's an x value. X equals r of y, and the y value is 2. That's the outer radius. And what about the inner radius in terms of y? We have it in terms of x. Right. The little radius, the little radius that's being hollowed out, or that is hollowing out the center, would be square root of y over 2. So the integral that would give me the volume would begin with what? Pi. Integrate x values or y values, which are 0 to 8. And then the question?
Little r of y.
Little r, oh, yes, thank you. Integrate over a range of y values, 0 to 8. Outer radius squared minus inner radius squared with respect to y. What is it, Major? Oh, stop it. Like a kindergartner, I'm going to have to move you away. All right, so far, keep breathing, I'm talking to myself, not to you. I got it. If my solid is truly a solid, then I'm only going to have one radius, and the volume is going to be pi times the integral of the radius squared d, depending on whether my rectangles are horizontal or vertical. It's when I have either a deep compression or a whole board totally out. This doesn't actually have a hole in the bottom when you rotate it. It's not like a total core has been removed. But if you think about what these cylinders would look like, they're cylinders with a hole in the middle. You know what you call a cylinder with a hole in the middle?
That's what that would look like.
The cylinders, I'm talking about the little bitty cylinders that are being added up here. If you imagine one of those cylinders, they are called washers. Because that, play like it's kind of rounded on the ends. It's a washer. Because it's this outer rim with a hole cut through the middle. And it would be a washer all the way down to here. The very bottom little cylinder wouldn't have a hole in it. It's got a solid bottom. It would hold whiskey. But this is, the washer method is actually kind of a special case of the disc method. You're still using disc, but they're discs that have holes in the middle. And by definition, that's a washer.
It sounds like a washing machine.
That's why it sounds like a washing machine in my head. I can't do the problem without hearing. All right, let's do another one. C part. How is it different? The C part, we have the same y equals 2x squared, and the same y equals 0, and the same x equals 2. But this is being rotated around the line y equals 8. The line, here's everything that's going through my head. The line y equals 8 is horizontal, so we have something that's going instead of. Y'all are fun. All right. So 1, 2, 3, 4, 5, 6, 7, 8. And then if it's going to be flipped around that, I wish I'd counted by 2s, but up here somewhere there's a 16. All right. There's the line y equals 8 that it's being flipped around. And here's my piece of parabola that's going to be rotated around that horizontal line y equals 8. So the other piece is going to look like that. And actually it hits y equals 8. Y equals 2x squared, y equals 0. Oh, it was supposed to be bounded by x equals, no, that's right. Bounded by x equals 2. Here's x equals 2 over here.
Should it be the other side of the parabola? Let's say the side that we use for parlay. The outside.
Ooh.
So it's like a little bowl in a cylinder.
Mm-hmm. Hold on 1 second, let me think. Okay. Yes, this was being bounded, they have the same boundaries, but this was being rotated around a vertical axis. This one's being rotated around the horizontal axis. So we have this whole parabola.
If you shade in that region bounded by the parabola at x equals 2, that's what you're trying to find, or trying to rotate around y equals 8, isn't it?
Yeah. It's the same region as in the last problem.
Okay. And once I shade that, I can see why this is going to take a washer instead of a disc. Before I shaded it, I was looking at rotating this part. If I was rotating this part around the line y equals 8, it would be a solid. There's no dip, no compression in the middle. But this same region, if I rotate it around the line y equals 8, then I can see it's going to, the cylinders are going to be washers instead of discs. All right, what's my outer radius being formed by? Yeah, the outer radius is that. What is my inner radius being carved out by?
2x squared.
Yes. And I do need functions of x here because I'm using vertical rectangles because I'm going around the horizontal axis of revolution. So the volume of that solid is going to be pi times the integral from where to where?
0 to 2.
Because I'm using x values instead of y values. 0 to 2 of outer radius squared minus inner radius squared with respect to x. You have a quadratic, a piece of a parabola, and a line. And we're going to rotate that in the A part, we're going to rotate it around the x-axis. Rotating around the x-axis means we're using horizontal or vertical rectangles. Got to be perpendicular to the x-axis. So notes I'm making in my head, vertical rectangle means the width is dx. And my function has to be in terms of x, and my bounds of integration have to be x values. So let's see what this looks like. I'm going to have to find where that parabola intersects the line. How do I do that? If I don't find bisect on my calculator? Yeah, just set them equal to each other. Oops, no, that's fine. Exclude. Yeah, minus 3x equals 0. 2 points of intersection. Actually, if I want, those are the two x values of the points of intersection. If I actually want the ordered pairs so that I can graph them, the easiest place to let x be zeros in the linear equation and you get y equals 4. You get the same thing if you let x be 0 in the quadratic equation. When x is 3, y is 1. So they intersect right here. And right here. From here to here, oops, that's supposed to be 3, 1. From here to here, you have a piece of a concave down parabola. And you have a line segment. So that's the thing we're going to be rotating. And when I try to picture what the whole thing is going to look like, if I rotate it around the x-axis, I'm getting a little bit better at flipping that upside down and seeing now the parabola part's on the bottom and the line part's on the top. So you're going to have this dish-shaped thing that actually is going to have a hole in the bottom because those two pieces don't meet. And that's the very best three-dimensional object I can draw. What's the outer radius? I'm really just looking at this piece I'm rotating. It's being, if you imagine this being cut out of a block of wood, the 4 plus 2x minus x squared is carving the outer shell of that bowl. And the piece that's being removed is cut out by the line. So the volume is going to be pi times the integral from where to where?
From 0 to 3.
Mm-hmm. We're integrating with respect to x. We're using x values, and the farther, the rightmost x value there is 3. So we're integrating from 0 to 3 of outer radius squared minus inner radius squared with respect to x. Jordan, is that okay? All right. How is the B part different? We have the same piece of parabola and piece of line. That intersect at 0, 4, and 3, 1. So that's still the thing we're rotating. But in the B part, we're rotating it around the line y equals 1. So here's the thing being formed. There's no hole in the middle anymore because those actually met at the point 3, 1. We're still rotating around a horizontal axis, so we're still using vertical rectangles. What's my outer radius?
Still the quadratic.
Minus.
Yes! Was that you, Aaron? No, Major.
It's both.
Both of us. That outer radius, if you just said it was the whole 4 plus 2x minus x squared, then you would have it going all the way down to the x-axis. And it's not going all the way down to the x-axis. So you have to say it's that quadratic piece minus 1. Or just negative x squared plus 2x plus 3. And then the inner radius would be what? Plus 1? Not plus 1. Did you say plus 1? Why? You have the line y equals x, but it's being cut off at y equals 1, so it's still minus 1. Sam, was that just a misspeak, or was there a reason you were thinking you'd add 1? Okay. So the volume would be pi integrate from where to where? Still going 0 to 3 on the x-axis. Outer radius squared minus inner radius squared.
So the -1 is for what?
To account for the fact that you're not going all the way down to the x-axis. Here, let me try to explain the difference between these two. This one, we were rotating around the x-axis, so that outer shell that was being rotated actually went all the way to there. And so I didn't have to subtract anything. I could have said the outer was this minus 0 because it was going all the way down from there to 0. This one is not going from here to 0. It's only going from here to 1. Is that okay?
Yeah, I think I got it.
Okay. All right, I have 2 more if we have time. Number 20. Y equals 3 minus x. Y equals 0. Y equals 2. And x equals 0, that region rotated around the line x equals 5. We're rotating around a line going, what's our axis of rotation? It's vertical, so our rectangles are perpendicular to it, horizontal, and horizontal rectangles have a width of dy. So we want everything in terms of y, and this in terms of y would be 3 minus y. All right, let's see the thing we're rotating. Y equals 3 minus x. When x is 0, y is 3. When x is 1, y is 2. When x is 2, y is 1. When x is 3, y is 0. I would go ahead and draw that line, but actually it's supposed to be capped where? What's its upper? Yeah, I'm going to stop it right here at y equals 2 because that's one of the boundaries that I was given. So this is actually, instead of going to form a triangle, it's going to form a trapezoid when you rotate it. All right, let me double check everything. My piece of a line, the y-axis, the x-axis, and the top portion y equals 2, that's what's being rotated. And if I rotated that around the x-axis, would it take discs or washers? Yeah, there wouldn't be a hole in the middle if I was rotating it around the x-axis. What if I was rotating it around the y-axis? Around the y-axis, it would still be solid. So it would still take disc.
So if the whole thing is, like if the whole shaded region is connected to the axis, it's going to be
That's beautiful.
discs.
Yes, yeah, if it's connected to the axis of revolution, there's not going to be a hole in the middle. But this axis of revolution is over here. And when I rotate that, it's going to be over here. Here's the outer radius. And then here's the part that's being bored out. It helps me if I only shade the part I'm rotating, not its corresponding part on the other axis of rotation, or on the other side of the axis of rotation. It's the part that I've shaded there that's being rotated. And you said I was using horizontal rectangles, so everything has to be in terms of y. And so my integral, it's helpful to write down the outer and inner radii first. What's the outer radius? Yes. Yeah. From right here to right here is 5. And when in my head, I'm hearing my washing machine, I'm seeing this whole thing going around and around. The outside is going to be like a band. And that circular band has a radius of 5. Now, what's the inner radius?
minus 1.
Wait. No, that's not all that's being cut out. When we're using horizontal rectangles, we have to, this will help. That outer radius of 5, think of it as right boundary minus left boundary. That's 5 minus 0 is what that 5 is. So what's this piece that's being cut out? Again, think right boundary minus left boundary.
5 minus 3.
Yes. Gotta have right boundary minus left boundary. That's just 2 minus y. 2 plus y. And so my volume will be given by pi times the integral from where to where. I just didn't hear you.
0 to 2.
I'm using horizontal rectangles. My bounds of integration have to be y values, and so I'm integrating from 0 to 2. Outer radius squared minus inner radius squared with respect to y. Yes, I did, because I have to end the day on a mistake. Or else you just wouldn't know whose class you had been in. Yes, I wrote that backwards. I said it correctly, but I wrote it wrong. Outer radius squared minus inner radius squared. All right, I had another one, but it wasn't vastly different than that. When you're setting up horizontal rectangles, always think right boundary minus left boundary.
So the right boundary would be formed by the axis of rotation in this
Yes.
instead of intersect.
Yes. Yeah. Alrighty, the homework is at the bottom of the handout. They're just 5 problems, but I think 11 and 13, 11 has 4 parts and 13 has an A and a B part. Have a good weekend.